compared to fluorescent lights. All right, well, I think the recorder is on. Let me just double check. Yep, it is. Should be recording now. Yep. So this is a, I didn't plan it this way, but since, I had all of these tabs open from my previous class, I just decided, hey, what the heck, you guys should probably know about these things too. Okay, does anyone know about this guy? Did anyone read the textbook from your cisp310 class? Okay, so he is the guy who wrote or invented, he created a C programming language. His name is Dennis Ritchie, okay? And what I pointed out yesterday with my cisp310 class was, look at his, when he passed away. He passed away on the 12th of October in 2011. Many people remember October 2011 because that's also the month when this guy passed away. Okay, so he passed away about a week before Dennis passed away. So did you guys remember when Steve Jobs passed away, when he died? Okay, it was a big news and people definitely talked about it for weeks to go, right? Did anyone remember this guy passing away a week after Steve Jobs? No. Do you guys even know who he is? Not really, right? Just some old fart, doesn't seem particularly, well-dressed or, attractive. Not like Steve Jobs, okay? But he's the guy who wrote, co-authored the original Unix operating system and created the C programming language. In other words, without him, Steve Jobs will still be, doing his design on paper. There won't be any Unix. Well, Unix, that's kind of like a mainframe operating system, right? Is it? Come on. Where do you find Unix these days?
In Jurassic Park.
Sorry?
In Jurassic Park.
In Jurassic Park. Yes, they actually have quite a few technical scenes with stuff on it too. Okay, how many people have an iDevice here? iPad, iPod, iPhone, iWatch. Those are all running what operating system?
iOS.
iOS. But what is iOS? iOS is based on BSD, and BSD is the Berkeley Standard Distribution of Unix. Okay, so that means without this guy, Steve Jobs may still be a genius, but he won't be selling computers or iPods or iPads or iWatches or anything like that. Okay? And we won't have C programming language either, okay? Which may or may not be a good thing. Okay? Because the guy, this guy and also his partner they were basically top tier programmers at the time, working for Bell Labs. And he invented the C programming language because he was sick and tired of writing the Unix operating system in assembly. The very same programming language that we'll be using in this class. But you guys will be writing homework that will be in the order of, I would say about 100 lines at the most, okay? Not even coming close to the complexity of an operating system. And he was using assembly, to program, Unix. So he just kind of got tired and, bored after a while and go like, oh, I have to make a better tool to write an operating system. So C was invented for his own use. It was never intended as an educational, type of programming language. Okay, it was just invented for himself so that he can finish the job quicker. Okay, all right. So nothing really too, important. Just these two guys, and most people remember, one but not the other one, who's actually more important in the history of computer science. But that happens all the time, right? All right, so what we'll do today is we'll go back to cisp310, and what we'll do today is the same usual thing that I do. I will introduce a new homework assignment, and then we'll talk about the components that we need to do this homework assignment. Don't worry about the X1, Q1. Those are the exams, quote-unquote, exam questions from previous years. But what we'll do is we'll focus on Music Box. This is your next homework assignment. It is due in a week, okay? And before I forget, I'm going to pass the row sheet. All right, so the question is, why are we dealing with a music box in this class? Well, it's not exactly a music box, okay? All it really is an automated mechanism to actuate control signals, okay? That's all it is, okay? It is important because it will form the basis of the additional homework assignments using Logic Sim. Because I'm lazy, okay? I don't want to use my own time to click buttons, on your design to see it work. I want it to automatically play itself, okay? That's what it is. Well, but it's also important in the other sense because this is the engine. This is at the very heart of your processor because it controls all of the other components in your processor so that you can execute instructions. That really is the more important reason why we have to deal with a music box. Okay. Does anyone want me to explain what a normal physical music box is? Okay. Very good. So we'll go ahead and just look at a music box, and there are plenty of pictures of a music box. So if you go to Wikipedia, it has a really good explanation of a music box. Some are really big and some are small. Okay, and let me see if I can find the design inside the music box. You get a good picture. That's a pretty good one. There we go. So this is a music box. It has a drum. Okay. So number 2 is a cylinder or a drum, and on the drum there are bumps. Okay, so the bumps are either soldered on or screws or something that makes it kind of stick out. Okay. Number 3 is kind of like a harp. Okay, but it's open-ended. Basically you have pins that are free floating. So when the drum rotates like this, and the bumps pluck the pin, it will make a sound. It will make a sound because of the vibration. Okay, and then it's winded also. So in this case, this one is not stored. It doesn't have stored energy. Somebody has to crank part number 1 the whole time in order for music to play. Is that okay?
Yeah.
All right. So obviously, I'm not going to crank anything with your homework assignment because that's the whole point, is so that I don't have to do a single thing to grade your homework assignment. But number 1 can be replaced by what we call a clock. Okay, and I will demonstrate what a clock is in Logic Sim. Okay, that's basically how I attach the crank to a motor for grading the homework assignment. The key is the drum here. Okay, how we specify the content, on the drum will determine what control signal gets played. Okay, who's going to be a 1, who's going to be 0, when do we change from 0 to 1 with which signal? That is all controlled by the bumps on the drum. Okay. Are we doing okay so far with the relevancy of a music box to what we are trying to do in this class? Is that okay? All right. So I'll go back and finish describing the homework first, and then we'll take a look at the Logic Sim components that you will need. All right. So this is the most basic form of automation. So in the homework assignment, we'll be specifying 0s and 1s. The what, we just kind of explained it. So in your homework assignment, we'll be using a ROM component, a read-only memory, which is actually easier to deal with compared to RAM. Okay, in the previous 2 lectures, we talked about how to use a RAM component. A ROM component, which is read-only memory, is actually easier to deal with. Can anyone just kind of guess why ROM is easier to deal with?
There's no wrong.
Exactly, there's no write, right? So if you're not writing to it, there's no clock either. It's always going to drive the data line. Okay, when it's enabled, it's going to drive the data line. Okay, very good. So if you know how to deal with RAM, ROM is easier. We'll also deal with a clock tick, mechanism, which is built into Logic Sim. You don't have to do much; just know which component to use instead of an input pin. The how is basically, talking about the drum. Memory is basically the drum itself. It stores the pattern to be replayed. And then the other main component is a counter. Now this is going to be a little bit trickier, okay, because a counter requires a register, an adder, and a feedback mechanism so that it can refresh and update itself with a value that is 1 more than what it used to be. Okay. And then these are the components. For this particular homework assignment, I want you to play with this particular component under the input-output devices of Logic Sim. It resembles an actual 7-segment display. If you don't know what it is, I'll show you a picture of that later on. But this is basically a really old school type of LED device where you can display digits from 0 to 9, okay? And a few other letters too. What it is it's 7-segment because there are 7 LEDs usually, but you can also find LCD versions of this. But each line is basically one quote-unquote segment. So by controlling which segment you turn on and turn off, you can display various digits and some letters too, but it's very, very limited. Are we doing okay so far with what a 7-segment display is? It has 7 inputs basically, okay? You specify the 7 inputs, then you can display 0, it's like that. 1 obviously is easy, 2, 3, and so on. Are there any questions about this? You guys look at this and go like, wow, that is really archaic. You have seen simulated 7-segment display on phones and whatnot. They have special fonts to do that. When I was a kid, the first time I got a digital watch that has a 7-segment display of the digits, it was like, wow, that is so cool. Yep. And we'll have a button, okay? So we use a button to reset the pattern, so it starts from 0. And you also need an OR gate, okay? Now this is the trickier one, okay? So we'll talk about why you need an OR gate in this entire design. All right. So we look at all these components, and we'll go to Logic Sim and experiment with these things individually, okay? And then you guys will have to think of a way to connect all of these things so that you come up with a implementation of something that only displays 0 to 9 repetitively. So it will display using the 7-segment display, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Are there any questions about the overall description of the homework assignment? Not so much the how, but in the end, what it is supposed to do. Okay, only 1 digit. Okay, you don't need to go for 2 digits, just a 1-digit design. All right. So if this is all done, we'll go ahead and start up Logic Sim because we want to look at each individual component, and you guys will start to think about how they're supposed to be connected in your homework assignment. Okay. All right, so this is the usual Logic Sim. The first thing I'm going to demonstrate is clock, okay, which is a very simple mechanism. Clock belongs to, well, kind of strangely, it belongs to wiring. So when you go to wiring, you see clock here, which is right under pull resistor. So drag it out and put it into your design. I'm going to magnify a little bit so we can all see a little better. It looks just like an input pin, okay, square, okay. Have the connector facing east, okay, and you can use a label to, okay, CLK is a typical way to CK or CLK are typical labels for a clock, but it really is not a pin because you cannot really control the 0 and 1 of a clock. That's the whole idea. Remember, I want to use a motor to do the crank, right? I don't want to use my own hand to crank and make the whole thing spin. So one way to look at a clock and say, okay, but why is it useful? Well, let's hook it up to something. And we'll go to input and output, and this time we'll just hook it up to a single LED. Okay, and LED, this is off for now. And what we'll do is we'll hook up these two, and we go to simulation mode. And in simulate, you can now control tick frequency. Tick frequency basically controls how frequently do we change the clock signal, okay? So how do we measure frequency? If you look at the time diagram of a clock signal like this, so the horizontal axis is time, and then the vertical axis is basically 0 and 1, okay? the clock cycle, a single clock cycle goes from a, you can pick either edge, okay? It doesn't matter which one you pick. But this is a rising edge, so it will be from one rising edge to the rising edge to the other rising edge. This is one clock cycle. Frequency is measuring how many clock cycles do we get per second. That's hertz, H-E-R-T-Z is the unit of frequency. Are we doing okay so far with this? So the way it's set up right now is 1 hertz, which means this will complete in 1 second. So every second we have a rising edge. Okay? The duty cycle is referring to how much time does it stay on and how much time does it stay off. In this case, the duty cycle is 50-50%. So it will spend half of its time turning on and half of its time turning off. Yep.
And where is that controlled? Or
the duty cycle?
Yeah.
The duty cycle cannot be controlled because most clocks have an even 50-50 split. Yep.
Actually, I saw something on the clock where you could change how long it's high and how long it's
Oh,
low.
okay, so you can actually control the duty cycle.
Yeah,
Okay.
it's defaulted to 1 tick high, 1 tick low.
Okay, thank you. All right, so let's go ahead and just turn this whole thing on. Well, we'll do this first. We'll use a debugger first, okay? So click. This is on, off, okay? But that kind of defeats the whole purpose. So I want to do this. You can see, okay, now my hands are not touching the mouse or the keyboard, okay? This is all doing it all by itself, okay? That's the basic idea of using a clock is it is autonomous, okay? You just set it off and it will tick. If you need to stop it, you can easily go to simulate and click, ticks enabled, and it will disable it. Okay. Another tool you might find useful because when you're ticking like this, you might want to find you might find logging, actually helpful. So you can basically add components that you are logging. And this is a table file. Output is disabled, and we can select the file, I suppose. Log, save, and now when we run the simulation, the file will be populated with the values of each tick. So I'm just going to go through a few rounds here and then disable it, and then we go back to my DOS prompt here or command line interface and take a look at the test log file, and you can see what the state of the 2 devices. A 1 is an on and a 0 is an off. Okay. Now this doesn't seem to be really important. But when your design gets complicated, this file can save you a lot of time because you may not be able to observe all the changes of all the components, okay, with your eyes. But when you go back to this file, which is a log of everything that goes on, it's very, very helpful. Okay, so I just want to show you the tools you can use to debug your design. Okay, are there any questions about a clock, which is basically the same thing as an input pin, but it can be automated, and in this case an LED, which is nothing more than, I could have used an output pin, but an output pin is boring because it only says 0 and 1. This one you can turn it on and turn it off. Are there any questions about this? No questions? All right. If there are no questions about this, we'll move on. And let's see, let's go back to the homework assignment because I want to go through all of these components. So we got the clock done, okay, that's the easiest one. And then the next one we'll do is we'll take a look at an adder, okay? An adder is pretty easy because most of you have implemented your 4-bit adder already, right? Okay. But for this particular homework assignment, you don't even have to use that, okay? Because I'm just going to cheat a little bit and use an adder component. Okay? This is an adder component, and in this case, I will leave it up to you guys to decide how many bits you need for the adder. Okay? The default is 8, okay? But you can change it. You can change it all the way down to 2 if you want to. Okay, not 20. I want 2. 2, come on. There you go. So now we have a 2-bit adder, okay, which means the input path is 2 bits and 2 bits. It can add two 2-bit numbers, and the result is another 2-bit number. And we have carry in, carry out, the same usual thing as your full adder, okay? Except this is not a single bit full adder, it is a multiple bit full adder, okay? All right, so let's take a look at what you can do. Before we do something with it, we have to identify, okay, but what are these connection pins, okay? This one is in one of the numbers to add. This is the other number to add. This is the input carry. This is the output carry. This is the actual output, or the sum of the two inputs. Are we doing okay so far with a 2-bit adder? Okay. So let's just say for now, I have no use of carry in. Okay. When you have no use for a particular input pin, it's always a good idea to give it a constant. Okay. In this case, I want a constant of a 0 because I don't want it to interfere with the actual calculation. So we'll turn the input into a constant 0, and I'll move this part out of the way. Okay, move this out of the way. Okay. The output, I can specify, it doesn't have to connect to anything, but I do want to specify what are the inputs and the output of this thing, just to show you, how it works. So we'll choose one input here, one more input here, and then we'll choose an output over here. And I'll let LogicSim complain about it, and because it is an important thing to understand why LogicSim is complaining. It has to do with all of these pins, the 2 input pins and the 1 output pin, they're all 1 bit wide, okay? But the adder is specifying 2-bit wide interfaces. Well, that's easy to fix, because what you can do is to go to each pin. Now, I should have done this before I replicated, but that's okay. You can change the number of bits, and you can see how now it is okay. So this is basically how LogicSim can do a sanity check of your design. And it's working already. It's basically telling you, right now, it's telling you 0, 0 as a binary number plus 0, 0 as a binary number is 0, 0. That's the output. Okay? And you can test it too. I mean, if you don't want it, you can play with this and test it. So let's go into simulation mode. It's telling you 0, 1 plus 1, 1 is 0, 0. Does that make sense to you? Okay. Or we can change it to 1, 1 plus 1, 1 is 1, 0. But with a carry. Okay, if you monitor the carry, you can see this is now in bright green, which means the output is actually a 1 for the carry out. Are there any questions about how to use an adder? And remember, it is up to you to decide how wide you want to make your adder. Okay? Is that okay so far? Yep, go ahead.
So we have nothing connecting to the CL, to the carry out?
In the music box implementation, carry out has no particular use. You can leave it unconnected. It's okay to leave an output pin unconnected because you're basically saying I'm not making use of it, but it's not okay to leave an input pin unconnected because then the signal is not specified. Okay. All right, so if this is okay, we'll move on to the next one, which is kind of an important concept. It's called a register. Okay, a register belongs to the memory category, but it's not exactly memory either. So we'll go ahead and drag a register out, and we'll take a look at the register. Okay, so this is a register. It is now selected. So when you look at the properties of a register, you can see that it has 8 data bits in this case. Once again, how many data bits you think you will need for your register is up to you. Okay, you will have to come up with, oh, I think I need this many data bits. Okay, so you have to make, you have to decide how many bits are actually needed in this case. Trigger in this case is a rising edge, which means when this pin, the one that looks like a wedge, okay, when that pin goes from 0 to 1, okay, the state of the register will change. Okay, label font, and those are only for display purposes, so they don't really have any functional value. So now when I hover my mouse pointer over the individual components or the ports of this component, this is the input. Okay, this is the input of a register. Let me just hover over again. This is the data stored on clock trigger. In other words, you can present a certain value on this port, but the state of the register will not change until we have a rising edge on the trigger, which is also called a clock. This little the wedge symbol here. Okay. I'll show you guys how to make use of it. This is the output. Whatever the state or the value of the register is constantly getting output or specified at the output port. Okay. Now it is 00 in hexadecimal at this point. So when you hook up the output to a 8-bit output pin, it would display all zeros. Is that okay so far? Kind of? Maybe? All right. Okay. And these two, this one is enable when 0 clock triggers are ineffective. In other words, it's a clutch. Okay. If this pin is a 0, you can present whatever value you want in the input, and you can clock it all day long, but nothing is going to happen because it is disengaged when this is 0. When this is 1, it means it is engaged. Okay? So when you have a rising clock and a wedge symbol, whatever is specified at the input port will update the content of the register and also update the output as a result. Is that okay so far? Okay. I already explained what this one is. That's called a clock or trigger. I hate it when the documentation is not self-consistent, because this says clock triggers, and this one only refers to it as a clock, but basically they were referring to the same thing. One is a clutch, the other one is the actual tick. Okay. And this one is a reset pin, okay, or clear. When it is a 1, the value of the register will change back to 0 regardless of the input. So this is a good way to reset your design so everything goes back to a known state. Are we doing okay so far with all of these ports? I will demonstrate how to make use of it, but I'm just making sure that you guys understand what each port does. Yep.
Is there any significance to the D and the Q and the EN?
EN is enable, and the D and Q are basically the conventional terms for the input port and the output port of a register. For this type of register, anyway. Yep. All right. So let's go ahead and give it a try. In fact, I'm going to give it a try using a 7-segment display. So I will drag a 7-segment display over here as the output. And then we'll specify something as the input. Let me see what would be good as the input. Well, TTY is fun, but it's a little bit too much compared to what we really want to do here. So I'm just going to use a regular input pin. We have to change the width of the input pin. So that's going to be our input. And in this particular case, we have 8 bits for the register. So the input pin will also have to have the same width of 8 bits. So we'll specify 8 over here. And okay, it doesn't. I have to move the entire design a little bit. Okay, there we go. All right. So the next thing we need to do is to specify: are we enabling this register? For the design that you're dealing with, we are kind of constantly enabling it. There's no reason to disable it. So I'm just going to enable it all the time. And to do that, we can just feed a constant 1 to it. So we just put a 1 and basically connect the 1 to enable. So it's always enabled in this case. Are we doing okay so far? Okay. The clock line, we'll connect the clock line to a button. Okay. So this way, we'll put a push button here. A push button has a default state. If you click on it, it has a default state. The default state is a 0. When you press on it, it becomes a 1. So this is a way for me to generate the rising edge, but without hooking this up to the clock signal. The reset pin is going to be a 0. So we'll just go ahead and, no, I take it back. We'll have another pin or another button to control the reset pin, just so that we can see what happens when we press the reset pin. And then the output is going to go to the 7-segment display. But now we have a problem, don't we? Because the 7-segment display has individual wires. Each port is blue, which means it's only 1 bit wide. But the output coming out of the register is how many bits wide? 8 bits wide. So now we have to split the 8 bits into individual bits to get into the 7-segment display. So I'm gonna zoom out just a little bit because I need a little bit more space to use the splitter. A splitter belongs to wiring, so we just get a splitter here. And by the way, a splitter will also do a merger, okay, so it can go in both directions. So we'll have to say number of bits for the splitter is 8 because we have 8 bits coming out of the register. Now we want to say, okay, but how many individual bundles do we want to split it into? We want to split it into 8 individual bundles because we want only 1 bit per bundle, 1 bit per wire coming out of the splitter. Okay. There are many ways to do this. Okay, the really obvious but difficult way to do this is to have multiple splitters. So the first splitter will split into 2 4-wire bundles, and then you take 1 4-wire bundle, split it into 2 2-wire bundles, and then you split each 2-wire bundle into 2 individual wires. You can certainly do that if you want to, but I'm just going to do it the lazy way. The lazy way is to change the fan out to 8.
Oh my God.
Yeah, that's kind of cheating, but that makes it easy, right? So now we have 1 wire per bit, which is exactly what we want. Is that okay? Now you have to remember how these wires are numbered. Okay, that is important. Bit 0 is the least significant bit, or the one that is at the right side, on the right hand side, and that corresponds to wire 0. Okay, wire 0 is the least significant bit. That becomes important because when you specify, I want to make the display look a certain way, it is important to know which one is which one. Okay. So now we'll go hook up these individual ones. Unfortunately, it is not documented which one is which one, so we'll have to do some experiments just to find out which one is which one. But that's okay. At this point, we'll just go ahead and do all the connections. So now your design, is entirely up to you how to do the wiring. The effect is I want you to display 0 to 9. Okay, so you just have to figure out a way to make it work. And you can see it actually looks kind of nice. Okay, there we go. All right. So now this entire design is all connected. It's time to play with it and test it, right? So we'll go ahead and change 1 bit of the input port of the register and see which segment gets lit up, okay? Oh, what's up here? Nothing lit up. In fact, the register is still 0 0. What is the
buttons?
I didn't clock it, right? Okay. So let's clock it. Okay, so now bit 0 controls the upper right vertical segment of the entire display. And then what do you do next? You try out the other one. Okay, I would just change 1 bit at a time. So this way it is pretty clear which segment is which segment. Okay, and this one is over there. This one is over there. Okay, do you see what I'm doing here? Okay. Now the period here is the other one. I'm guessing this is the most significant bit. There we go. Okay. Now in your design, you don't have to deal with the period. Okay, so that means you can leave that one unlit. Okay, the entire time. Are we doing okay so far with how to control a 7-segment display using a 8-bit number? Is that okay? All right. Well, do we know how to use a register? Now, if you are debugging your design and you just say, I want to just plug a value into the register, you can actually do that. When you, in simulation mode, if you click on a register, you can type right away, a hexadecimal number, and that will become the actual content of the register, independent of the input or the clock line. Okay, so that makes debugging a lot easier. So you can just type in, like BF. Okay, there you go. So BF turns on those particular segments. Or if you type in, I don't know, I'm just giving myself some random values here. A5 is this. Okay. I still remember, these, kind of characters. In the early day Casio calculators, they used to have games that you can play on the calculator, and I think there's one game where you can control which one of the 3 horizontal segments to turn on, and you can hit a fire button. So the incoming objects will also be either the top or the middle or the bottom. So if your projectile matches the incoming bogey, then it will cancel out. But otherwise, it will just pass through, and you just wasted time, and the bogeys will keep coming at you. So you have to kind of press the button to control which line to fire, and then hit the fire button, and the speed ramps up as time goes on too. Maybe we can make that game as your next homework assignment, but not for this one. Hey, if they can do it with a Casio calculator in the 80s, we can certainly do it in Logic Sim. Okay, are there any other questions about a register, the buttons, or a 7-segment display, or a splitter? I'm just, recombining the components that you need to use in your homework assignment to do some kind of random stuff.
You didn't use the reset button.
I did not use the reset button. Let's go ahead and try the reset button. When you press the reset button, the content of the register will reset all the way to 0. There you go.
But not the input.
But not the input, because the input is something else is specifying the content of the input pins. So the input pins are independent to the reset line. Okay, are there any questions about this? No questions? Okay. Next one is, how do we use a ROM? Okay, a ROM is, as I said, easier to use than RAM. So it belongs to memory as well. Here's ROM. I'm gonna slap it down here and scroll down. There we go. Okay, and so when you look at a ROM, it only has a few properties for you to set up. The address bit width is basically the same thing as the address bit width of RAM. It controls the number of locations on the ROM component itself. So right now we are specifying a width of 8. With an 8-bit address bus, we can address 256 locations. So we have exactly 256 locations here. In the music box analogy, the address bus width is controlling the size of the drum itself. In other words, do you want it to play for Elise, which is a fairly long and complicated piece, and you need more space on the drum to do it. So you will need more address bus width in that case. Or do you want it to just play, Mary Had a Little Lamb, which is a shorter piece, right? So you can settle for a smaller piece of ROM. Okay. So in your case, you only need 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 locations. Hold on a second here. 10 is not a power of 2, right? So you have to think about a way to deal with that. Okay. Okay. Are you guys getting an idea of how to do it? It has to do with the output of the ROM. It has to do with the register, because your purpose is to reset the register back to 0 at the right time. And what pin of a register can reset it back to 0, regardless of the input to the register? The reset pin, right? Is there a rule saying that the reset pin cannot be coming from the ROM? No. There you go. So hopefully that will help you with your design. Data bus width, okay, this is actually the width of the data bus, is controlling the number of bits per position, per location. In the music box analogy, this is controlling the number of notes, okay? that the music box can play. Okay, if you have a piece that only requires 1 octave, okay, then you only need like 12 pins to play 1 octave. On the other hand, if you have a complicated piece where it spans over, let's say, 5 octaves, then you will need a wider data bus because it has to actuate at least one of the 5 octave pins, with the notes. Okay. So in your case, your data bus width has to control the 7-segment display, each segment of the 7-segment display, and on top of that, something else. Okay. So you have to decide, what is the actual width. Both of these can be any number. In other words, they do not have to be powers of 2 because the actual number of, so you can have a 7-bit data width if you want. Okay. For the address bus, same thing. You can have a 3-bit address bus. Now with a 3-bit address bus, how many locations can we deal with in this ROM? Only 8 locations. Very good. Okay. So that is going to be helpful. Are there any questions about this particular design? No questions? Okay. Let's go ahead and play with this. Okay, we'll play with this ROM, a little bit here, just so that we can see, what we can do with ROM all by itself. So once again, we specify an input pin, and we'll go ahead and change this. Well, 3 is okay. We'll just go ahead and use that as an example. So this goes to the address bus, and the output of this, let's see. Data bus width is 7 at this point. Well, that's okay. We'll just use 7 here, and for this particular thing, we'll just go ahead and use an output pin to display the actual output. So we have 7 pins, 7 bits here to match the width of each location. Okay, and select is basically saying, okay, is this chip enabled? For the purpose of your homework assignment, you can always enable it. There's no particular reason to turn it off. So we can just use a constant of 1 to always enable this particular ROM chip. There we go. Okay. So now we have the overall design to demonstrate how to use ROM. And you can see this is quite a bit easier compared to the RAM chip, right? Because the RAM chip has got the load, the clock, and you have to kind of think about, okay, is the data bus, what is the direction of the data bus? Is it driving the data bus, or is it sampling the data bus? In the case of a ROM, it's always driving when you have the chip enabled. Okay, so the next thing you have to do is to say, remember, this is the drum of your music box, which means you have to change the content of this thing to make it work correctly. You can change it on the fly like this. Okay, you can, if you go into simulation mode, you can go to one location and you can change the location, content to, let's say, 2E over here. That's okay. But this is a pretty, long way to do it. Okay, especially when the width is increased. You can right-click on the ROM component, and then you can click Edit Contents, and this will give you an editor to do it. Now, this is a really tiny editor because I specify the data bus, but the address bus to be only 3B wide, so there are only 8 locations on this ROM. Is that okay? But in your case, 8 will not be enough because you need 10 digits. Okay. So, but the more important part is once you change these locations. Okay, let's say this is 1, 3, and this is 6, 7 here. You can click the Save button and actually save the content of ROM into a file. Now that is important because you don't want to lose track of your ROM content, or you might want to load different ones, okay, depending on what you want to do, or you're debugging your design, you want to save one, and when you try out the other one. So you can save the content of your ROM and just save it using a file name. Okay, so I'll save it as this is some random stuff, and I just use ROM as an extension, and now I can retrieve that later on. Okay. Are there any questions about specifying the values of ROM in Logic Sim? Okay, I hit the close button here, and I didn't save the other one. I think I need to. it's not effective. But it's not getting changed here. Okay. All right, so when I change these pins, you can see that it's changing which location I'm addressing. This one is 100 because it's at location 4. So 100, and you can see the output pin is reflecting that. Unfortunately, when I look at the content, it is not consistent with what we are seeing. Okay, let's see if I can. Oops, I won't do it. Okay, let's right-click this and then say load image. That's it. So you can save and load image here. So we'll go ahead and load image random.rom. There we go. So you have to use the load and save image feature to get it back. Can everybody see how 67 is specified as the output, as a 7-bit number? 6. Okay, let's do the 7 first because we want to read from the least significant digit. So we look at this. It doesn't sense. 67 should be the output at this point, and the output. Let me just double check. The width of the ROM is 7 bits, so this is exactly 7 bits, and it's supposed to be spitting out 6.7, but that's not 6.7 at all. Not even close. Well, if Logisim does something like this, it's time to close it and reopen it. And I'm not kidding, it does have bugs, okay? So it's buggy. So we'll just use today's date, which is 2015-09-10. And just close it and reopen it. Recent. Here we go. All right, let's do this again. Okay, 100 is what we want, and this one is correct because 110 is 6, 0111 is 7. So just keep in mind, Logisim does have bugs. Occasionally, what you think it should be doing is not what it is doing. In that case, close it and reopen your file. Most of the time, that will solve the problem. Are we doing okay so far with how to use a ROM component? Is that okay? All right. Let's go back to the web page here. So we talked about how to use a ROM component, a register component, an adder component, a clock component, 7-segment display, a button, or 2 buttons in this case, and an OR gate. Okay, we already know what an OR gate is, so there's no need to explain how to use an OR gate. Okay, what if somebody says, but Tech, you didn't, somehow when I do my homework assignment, I kind of forget what you said in class. What do people do? What do you think people should do when they encounter problems like that, when they're doing their homework assignment?
Watch the video.
You can watch the video again, but that's going to take too long. I don't want to do that. Google can help, okay, but there's something even closer.
Oh, the manual.
Oh, the
Help.
yeah.
Yep. Go to the library, and in this case, this is organized exactly the same way as the categories when you select the components. In other words, it's ordered exactly the same way like this. So let's say, I need to refresh my memory of how to use a register, okay? So a register belongs to memory. You click register here, and this is a full explanation of the behavior and the pins or the ports of a register. Okay, so this is the quickest help. Okay, if I have any questions, I would have gone for the help. Now, what if this is not enough? Because the explanation is pretty much static, right? So what do? You design something like what I just did today. Okay, something simple, just play with it and confirm your understanding of the behavior is correct. Is that okay? All right. Cool. All right. So do you guys have a general idea of how to go from here? Now that we have explained, I have explained the components by themselves. I have explained what the behavior of your design really should do. Do you guys have a general idea of how to do it? Okay, so if I were to prioritize, and make this design, there are several things you can work on. They're kind of like even. It's not important which way you go first. You can go for the counter first. Okay, just make a counter mechanism, so it can count from 0 to not 9. Okay, it will count from 0 to whatever the width of your register is, and then back to 0. Okay, so it will just keep ticking, but make it automatic. So hook up a clock pin to somewhere within that design, so that for every clock, the counter or the register will count up by 1. And then when it clocks again, it will count up by another 1, and so on. Is that okay? So that would be one important component, kind of self-contained. The second component, which is also kind of self-contained, is the ROM itself connected to the 7-segment display. So you will have to figure out what value to specify in each individual location in the ROM, so that the display will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back to 0. Okay? So that would be, so these two can go on kind of at the same time. Okay? How these two pieces connect? Well, you look at the output of the register, and then you look at the quote-unquote input into the ROM, and you have to figure out how those two pieces connect. Are there any questions about my suggestion of how to proceed with this project? Yep.
Do we have to make any sound?
Hmm?
Do we have to make any sound? Or
Do we
just
have to
display the number?
Do we have
To make any sound, because the
do we have to make any
sound.
Noise.
The music box.
music
There's a
box?
music
No,
box?
no sound. Just 0 to 9. The music box is just an analogy, so you know what the design looks like. But if you look at input-output, there are other devices too, like a TTY or what we call a teletype terminal. So, yeah, but we're not going to go for that. Okay, we'll just do the usual stuff. Just the 7-segment display. All right. Are there any questions before we continue with additional topics? This is your homework assignment. You have 1 week to do it. Okay. The important part is you have to understand for certain components of these, the output will eventually come back to the input. So there are quote-unquote loops in designs like this. Okay. Are there any other questions? No other questions? All right. If there are no other questions, then I'll go back to my own notes here. Okay, if you can think of a question before the class ends, go ahead and ask those questions. And I would also strongly suggest that you use today's lab time to get a head start on this project. Okay, just go ahead and pick all of those components. Just play with those components. Okay, just to make sure that you understand how each component works. The register and the adder, those two are closely related in this particular design, so you want to find out how to get those two to work together as a unit. Okay, so you have some work to do during the lab time today. All right, so with the homework kind of out of the way, I will continue to talk about but why do we even need registers in a processor? Okay, that's the next question. So I prepared, and this is my note to do this. And by the way, my processor design is already on, so you can always refer to that if you think it might be helpful. Okay, so we'll talk about the registers. I'm just showing you this so that you know where to find the notes. Okay. At this point, when we kind of look back into what I have taught up to this point, we started off with transistors, okay? But transistors are nothing more than valves, okay? They are valves where the output of a valve can be used to control the input of another valve, okay? That's the basic idea of transistors. From 4 transistors, 2 N-channel MOSFETs and 2 two p-channel MOSFETs and two n-channel MOSFETs, we can make a NAND 2-gate. Okay, that was one of the first things that we talked about. But a NAND 2-gate can be used to make a regular NOT, a regular OR, and a regular AND gate. Okay, we talked about all of that stuff, right? And then after that, we talked about number or value representation. Particularly, we talked about binary numbers, because inside a computer, a modern digital computer, transistors are either on or off. Okay, and then we talk about binary arithmetics. We talked about binary addition. We talked about binary subtraction. And then we made that bridge. We made the bridge to say, okay, arithmetic operations are basically based on values. Okay, 1, 2, 3, 4, and so on. But then we have logic gates that only work on Boolean or zeros and ones only. So how do we get those two to talk to each other? Then we talked about the half adder and the full adder. And you guys did the homework assignment on the 4-bit adder, and now you have the homework assignment on the 4-bit subtractor, right? Okay, so we made all of those connections. In other words, if you want to plot a little chart of what we have talked about, we went from transistors to gates. From gates, we go to adder and subtractors. Okay, so we are increasingly moving away from the physical layer of computers and moving more closer and closer to what we are used to. Okay, we want to specify, we want to tell the computer how to sort an array and stuff like that. So we're getting closer, okay, because now we know how to add, we know how to subtract, and by the way, once you know how to subtract, you also know how to compare, which is a very, very important part, because the result of a comparison can be used for branching. Okay, should I go here or should I go there to continue execution? That's usually somehow related to subtraction. Okay, so this is all useful stuff. The ALU, or the arithmetic and logic unit, has multiple things to do: addition, subtraction, and stuff like that. With more advanced designs, they will also do division and multiplication in hardware. But in very simple design, simple processors, all they can do all day long is just addition and subtraction, because that's all you need in order to do multiplication and also to do division. Well, along with bit shifting, okay? Because you have to be able to move bits around a little bit. Okay? Are there any questions about how we are progressing at this point? So from adder and subtractor, we then move on to ALU, which is basically a whole bunch of adders and subtractors. They're just pathways to do calculations. Okay, very good. So now at this point, we want to say, but what about the values that we're computing? Where are they coming from, and where do we store the result? It's useless if you can do all the calculations, but there's no way to give your adder the information that it's supposed to add, or to extract the sum that you have computed, right? Then we talked about memory. Good. We can store all those numbers in memory, and we can store the instructions into memory. But there's one drawback with the concept of a memory. It is very far away from the processor, in terms of the gate level and time. So it's not efficient. If you have to go between memory and the processor for all operations, it's going to be very slow. We talked about this last time. Okay? And that's why we need registers. Okay? The registers are basically they can store numbers, they can store individual bits, but they can keep up with the speed of the ALU. Okay, if you think about this room as a processor, okay, this is the processor die, and each one of you is a processor core. Okay, this is what I used last time as an analogy. Okay, so we can kind of change that a little bit and say that each one of you is an ALU. Okay, you are a arithmetic and logic unit, and we'll make it a simple one. So all you know what to do is adding and subtracting numbers. Is that okay? So I'm the controller of the processor. I'm the one who's ditching out your work and go like, okay, you add these two numbers and give me that result, and you add those two numbers and give me the result. Okay. Without the concept of a register, the only way I can get numbers for you guys to add is to go all the way to the library. And in each trip, I can only get one number. Okay? And there are how many of you here in the room? 30 something? Okay? So you can probably imagine if that is the way we work, most of you will be just twiddling your thumbs, texting your friends, listening to music, and doing nothing. Not because you're lazy, but because I cannot give you enough work to do. Is that making any sense? Okay? So registers can solve this problem, because what registers are, they kind of like Post-its. Okay? So unlike a book or a binder in the library, which is really far away and difficult to get to, in this room I have pieces of Post-its, and you guys can just pass your Post-it to the next guy. Okay, so when you're done, so I can tell you and say, okay, when you're done with your calculation, pass the sum of those two numbers to the other ALU. Would that take long?
No.
Would it take even close to the amount of time for me to go to the library to store that number and then come back with the same number to give it to the next ALU? No, right? It's like instantaneous. That is why we have registers. I mean, kind of understanding the general idea of why registers are useful. But then why do we still need a library? Can't we just keep all the numbers and everything we need to process in this room as Post-its? We can't, okay? Because there's way too much stuff we need to store in order to execute a program, okay? Cache memory, well, let's get back to registers first. Registers are quote unquote expensive. In other words, they use up a lot of resources. Okay, in order to have a 32-bit register to connect to all of the ALUs, it takes up a lot of resources on the processor die. Most importantly, it's not just the memory to store the individual bits. It's using a lot of routing resources because the register has to be connected to all of the ALUs to be useful, and that uses up a lot of routing resources. Okay. So that's why we can only have a certain number, a small number of registers on the processor. The Intel processor, the i5 and i7 processor, in terms of general purpose registers, it only has about 8, okay, which is not a whole lot. Many other designs, especially RISC designs, reduced instruction set computers, they typically have 32 registers or more. Okay, so the Intel processor design using a cisp architecture actually has less or fewer registers compared to other architectures. But nonetheless, the idea of using registers is still the same. Okay, this is how we can get to the result of calculations really quickly. There's no delay whatsoever. When we are done with adding two numbers, the result can be immediately used by another ALU through the use of registers. Is that okay? But we can only have very few of these because they are very resource intensive. Are there any questions at this point about the necessity of using registers? And the registers that we talk about here on these slides, they are directly related to registers that we just saw in LogicSim. Okay, so you can probably imagine in LogicSim. Okay, let me just switch back to LogicSim here. If I want to design a processor using LogicSim, I'm going to use the registers inside the memory category. So each register, of the design is going to be one single register component from here. There are processor designs with only like 2 or 3 registers, but that's not going to be very helpful because that means you only have like 2 pieces of Post-its within the entire classroom. So there will be a lot of contentions, right? Because everybody wants to use the Post-its to pass the result to the next ALU. So that's why most modern processors have multiple registers. Are we still doing okay so far with this whole idea? Okay, switching back to my notes. So this is basically just where you find registers, find a discussion of registers. Can somebody still remind me of what the processor executes? What do those instructions look like to a processor? They're all zeros and ones. Very good. Okay, but there are patterns to the zeros and ones. So let's take a look at one particular instruction, and I'll just go ahead and search and look for one. So we'll look for the Intel x86 add register instruction, okay? Because that's the easier one to I understand. Okay, this is the add instruction, and I'm looking for particularly a representation here. This is real mode. This is good. Okay, I need to find out the /r. That's A. Okay, so this is the actual instruction. The instruction is, hey, that's not binary. Well, that's only because binary numbers take up too much space. So what do we use instead? Hexadecimal numbers. So 6601 and that little strange /r is actually the bit pattern that you need to specify. I want to add the values of two registers and store the result of the sum to one of the two registers, the second one. Actually, it's the first one. It's the first one that you store into. Okay? So in this case, the bit pattern is going to be 6 is 0, 1, 1, 0. So we have 0, 1, 1, 0, 0, 1, 1, 0. This 0 is 0, 0, 0, 0. This one is 0, 0, 0, 1. And then the third byte is used to specify which two registers we're going to deal with. Okay? Who is, out of the 16 possible registers, which two are we choosing for this particular instruction? Okay. So when you look at the entire bit patterns, I'm just going to show it on the board here. We have 0, 1, 1, 0 for the first 6, 0, 1, 1, 0 for the second 6, 0, 0, 0, 0, 0, 0, 0, 1, and then we have 8 bits in order to specify the two registers. I'm going to choose different colors here. So we have A, 4 bits, and then we have B, 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 to select which two registers am I going to add for this particular instruction. So this is the main reason why once an architecture has determined the number of registers, you can't really change it. Because if you change and say, oh, we want to move on to 32 registers, this format won't work anymore. Because we only have 4 bits within the instruction to choose one out of the 16 registers. Even if your architecture now has 32 registers, you cannot select the 32 registers. You can only select 1 out of 16, not 32. Is that making any sense? Oh, but we can make the instruction longer, right? So that we have 5 bits to specify each register. But that means one really important thing. What is the downstream consequence when you change these bit pattern here? Step into the shoes of Microsoft Corporation and think.
It's not going to work. Isn't when you try to switch this 32-bit system to a system for something like that?
Not exactly. Okay, so let's say I change this instruction. So I'll change the instruction and say, well, you know what? We'll change this bit pattern here. So this one is going to be 1, 0, and then we'll also shift the A, B, 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 B over a little bit. So we'll use A, and then B, 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 B for the rest. Okay, B, 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 like so. So we have 8 bits here and 8 bits here. So the instruction is still the same width. Okay, I'm just rearranging the bit pattern a little bit here. Okay. The question is, what is the consequence of doing this? If I have an operating system, applications and whatnot, programs compiled to work with the old architecture, will it also work with the new architecture?
No.
No. We have just lost what type of compatibility? Backward compatibility. Okay. Now, backward compatibility allows basically, all the new computers, okay, all the new i5, i7 computers, they can still run DOS. And when was DOS developed? In the early 80s, right? Okay, so we have backward compatibility. All the processors along the x86 line, they have backward compatibility all the way back to the x86 architecture, the very first one used in personal computers. Okay, but if you change it like this and you say, oh, we can use 32 registers, that will actually help improve the performance of computers. But the moment you switch to 32 registers, you have no choice but to change the instructions to accommodate so that you can select 1 out of 32 instead of 1 out of 16 registers. And that immediately will cause backward incompatibility, which also means all the operating system that you have installed at this point, or all the like Windows 10 that you purchase off the shelf or download, is not going to work for the new architecture anymore. What needs to happen in that case?
Firmware update.
Not firmware. This is actually a lot more dramatic than just firmware update. If you change the architecture so it does not have backward compatibility, you will have to redo everything. Okay? The BIOS needs to be rewritten. The operating system has to be, at least a good portion has to be recompiled, and a certain portion has to be rewritten as well, because every operating system has about 5 to 10% of code that is actually written in assembly. So that code has to change. Okay, the C code, well, you can just recompile for the most part. Okay, but it's a major undertaking when cross compatibility was not built into the operating system itself. Okay, what is one strength of Linux? Kind of related to what we are talking about here. Okay, we know it is open source, right? Okay, open source means what?
Free. Everyone sees the code.
It means it's free and free. Okay, the first free is in free beer, and the second free is as in freedom. Okay, yep.
I was always told open source doesn't mean it's free, because you can have open source that you have to pay for, but you can look at the code.
No, open source means the source code has to be made available to anyone, and you will also have the tools to compile the source code. So it really is free as in free beer. But on top of that, which is also just as important, as free as in freedom. In other words, I can take the Linux source code, okay, and go like, well, you know what? I want to make some tweaks to it. I can tweak it, okay. In fact, I don't even have to release my tweaks unless I want to make it available to at least one other person. But if I make it available to one other person, I will have to make it available to everybody. Okay, that's the spirit of open source. But why is it important in this topic? Okay, now people come up with new architectures, all the time. Okay, if you go to graduate schools of major universities in computer science, they experiment with all kinds of new processor architectures, new designs, and whatnot. So how do they get an operating system working with these new architectures that are not even on silicon yet? Okay, they're basically just theoretical. Imagine a much more complicated of logic sim that is capable of simulating complex, powerful processors. That's how they can test those processors. But they can actually make Linux available to those theoretical processors before the processor is even on silicon. And that's because of the open source nature of Linux. And Linux, for the most part, is written for that type of portability. So the majority of the operating system is written in C and C++. Well, just C, not C++, in a way that it is very portable. A very small portion of Linux has to be written in assembly because it is architecture dependent. But when you want to port Linux to work on the new architecture, you can recycle 95% of the code. There's only 5% or less code that you actually have to write in assembly that is specific to the new architecture. And that's why, when people are testing new architectures, it's very easy to use Linux. In fact, there are many cases where, the software, the operating system beats the hardware to the market. They can actually get the operating system working before they have to die. Okay? But what about Windows? Yep.
But does the Linux require additional drivers for certain hardware?
The answer is yes, but if the drivers are also written mostly in C, you can just reuse it. Okay, for instance, okay, let's say you want to use the RT2800 USB chipset on your new architecture, okay? But the chipset itself has been around for a long time, so the driver code of the chipset is already done, okay? It's already written in C, okay? So when you have your new computer using your brand spanking new, your super duper architecture done, you just have to take the source code for that particular driver, recompile. Well, you also have to retarget. I missed one part. You have to retarget GCC as well. GCC has a backend, so you have to make GCC generate code for the new architecture. But that's also something that's relatively easy to do, because GCC, just like Linux, is also designed for portability. So you can retarget GCC and say, I don't want to spit out x86 code anymore. I want to spit out Spark code, or I want to spit out ARM code. It's easy. Well, relatively easy, but it can be done without spending a lot of time. Okay, so that's why the Linux and GNU tool chain is used a lot when people have to deal with new architectures. Okay, I want to show you one thing. I know we are close to 1020, but not quite there yet, right? Okay, so we want to look at Debian distributions, because I want to show you what architectures are supported. And it's usually somewhere around here. Okay, we can just look for Linux kernel, Linux image. So no, that's not what I want to do. Search. I'm just trying to search for the search page. Linux image. There we go. Okay, so this will locate all of the major distributions. Okay, the last part are the architectures that are supported. So AMD 64 is actually the new Intel 64, 686, Spark 64, System 390, which is an IBM mainframe architecture, PowerPC 64, PowerPC itself, McKinley, I have no idea what it is, Itanium, nobody uses that anymore, but it is still maintained, and many other architectures, Versatile, Spark, ARM, and so on. So in other words, you can actually find Linux available for most modern architectures. Okay, and that's because of what I just talked about. But this also has something to do with what we just talked about here. Is you cannot change after the fact. It is very difficult to change the architecture to make use of more registers, and that's because the way you specify the registers is hard-coded into the core of the instruction set itself. And you cannot change that just because, oh, we want to double the number of registers. You can't do that. All right. Are there any questions at this point? Okay, if there are no questions, I'm going to end the class a minute and a half earlier. And then we'll go to the lab at about 10:30. For those of you who want to get a head start on the homework assignment, I think it's a good day to get started.